going to talk to you about nested virtualization for ARM, but I'm going to start with a little bit of a disclaimer. This wasn't actually my talk. I inherited it from Tech Lead. So I'll do my best to get through this stuff. But if something becomes unclear along the way, please just interrupt me, raise your hand, and I'll try to clarify. It's going to be a pretty technical talk. I'm going to assume that you know what an operating system is and what virtualization is. But I'll try to cover as much ARM stuff from the ground up. So this is really shared work between Linaro, Columbia University, and ARM. So the guy who did the most work is Tech from Columbia. And I worked on it, Shiwei Li, Jason Ni worked on it, and Mark from ARM worked on it as well. I'm going to cover the basics of virtualization of nested virtualization on ARM. And I'm also going to get into what ARM is going to do for their next release of the architecture and how we're going to improve performance by changing the architecture. So nested virtualization in its essence is the discipline of running VMs inside VMs or hypervisors on top of hypervisors, or how you prefer to put it. So the way you do that fundamentally is you run a hypervisor inside a VM already running on top of a hypervisor. So already at this point it should be pretty clear that we need some terminology to be able to talk about this. So there are different ways of describing the different levels of hypervisors in VM. But I'm going to call the first level hypervisor for the host hypervisor. And VMs that run on top of the host hypervisor, I'm going to call that just VMs. And then a hypervisor running inside a VM becomes a guest hypervisor. And a VM running on top of a guest hypervisor becomes a nested VM. Okay? There are a number of use cases for nested virtualization. Some people have thought that it's just a curiosity, but it seems like it's getting more and more used. If you have guest operating systems that use virtualization for basic OS features like security enhancements or for backwards compatibility, if you want to run those guests in your VM, you really need nested virtualization because they might embed a hypervisor. There are also companies that allow you to take an existing private enterprise cloud infrastructure that already uses virtualization and host that on another cloud. So you're going to run hypervisors on hypervisors. And people actually do that commercially. Testing and debugging are important cases. It's really good to be able to run automated tests, or for developers to run hypervisor development on VMs instead of crashing their laptops and that kind of thing. And what I really like is that you can now get an ARM VPS instance for €3 a month. And I think it's really cool if students and such who don't have access to expensive ARM server hardware, for example, could go and develop KVM ARM stuff so that I don't have to do it. So just a brief sort of look at how virtualization works on ARM. ARM provides 3 basic CPU modes. For those of you who went to my talk this morning, you may already know this. So you have EL0 that runs user space, you have EL1 that runs the kernel, and you have EL2 that runs the hypervisor. So even for KVM here, I'm just going to talk about KVM being a hypervisor running in EL2 and assume VHE. But really the core of running guest hypervisors on ARM is the discipline of emulating a virtual CPU that now has a notion of virtual EL2 in addition to its EL0 and EL1, because we want to run unmodified guest hypervisors, and those are really written to run in EL2 on ARM. But the question is, which hardware mode are we actually going to run your guest hypervisor in? We cannot run it in EL2 because we will get the same level of privileges that the host hypervisor has. So our choices are really between EL0 and EL1. You can actually run guest hypervisors on ARM 8.0 in EL0, and you can do trap and emulate. But it's terrible. It's really, really hard to do in the host hypervisor. It's really impossible to provide proper virtual memory semantics, and it's going to be awfully slow. So a much better alternative is to run it in EL1, similar to what you run the kernel in, because EL1 and EL2 are actually quite similar in terms of their actual runtime. But the problem is that that doesn't work on ARM v8.0, because if you try to do EL2 specific operations in EL1, they don't trap to EL2 so that your host hypervisor could emulate them. They just create an exception locally at EL1. So that would just crash your guest hypervisor. So ARM realized this, and they fixed that in ARM v8.3, where they provide nested virtualization support. What they do is they provide you the minimal set of features that you need to do trap and emulate a virtual EL2 inside your VM, running your guest hypervisor in virtual EL2. So the way it works is you get an extra bit in the hypervisor control register, and when you set that bit, you get to trap EL2 operations that wouldn't otherwise trap to EL2. You also trap ERED instruction, so that's the exception return instruction to EL2. And that's really an interesting one, because normally an ERED is something you'd execute in EL1 to return either to EL1 itself if you took an exception from the same level, or to EL0 where if you took an exception from user space. But now when you've set the nested vert bit, then you'll actually trap when you try to do an exception return, and then you can emulate the exception return in software. And finally, if you try to ask the hardware, you read current EL, it's an instruction that tells you which exception level am I running in, the hardware will lie to you and tell you you're in EL2 even though you're really in EL1. So in terms of implementing basic support for nested virtualization on KVM ARM on 8.3, we have to do at least these 4 things. We have to somehow emulate EL2. We have to provide stage 2 MMU virtualization. We have to provide a virtual hype timer. And we have to support nested virtual interrupts. So the first thing we do is we figure out a way how to describe our EL2 state in memory. And that's pretty simple. Right? We have a description of system registers, which are the EL1 registers for a normal VM. So now we add EL2 registers. Fine. Now we can describe it in memory, but then how do we actually run something with it? Well, normally when we run a VM, what we do is the host hypervisor will take all of this EL1 system register array, and it will write each system register into the real EL1 registers. Right? And then you do an exception return into the VM. And when you go back, you save all the hardware state and put it back into memory. With nested virtualization, we might be entering, whenever we enter EL1 to run the kernel, we might be entering a VM kernel, or we might be entering a guest hypervisor. Okay? So if we're entering a VM kernel, we'll put our EL1 state into the hardware. But if we're entering the guest hypervisor, we have to somehow emulate the behavior of EL2 in EL1 and put something else into the registers. So making this whole thing work relies on defining a mapping of EL2 registers into EL1 registers. Okay? So there are some registers where it's really trivial. You have like the translation table base register. It's basically a base address. So your guest hypervisor will have written something into its virtual representation of your EL2 page table base register. And what you do is you just take that value, put it into the EL1 register, and run it in EL1 instead. And it just works. Then you have other things like the system control register, which has different bits moved around with different meaning. And what you have to do is you have to actually write some code that says, okay, this is what the guest hypervisor was trying to create in terms of an execution environment. Let me translate that into an EL1 value that I write into the hardware that creates a similar execution environment. So we arrive at this concept of shadow EL1 registers, and I chose the name shadow EL1 registers because it's similar to shadow page tables. So it's really a copy of your EL2 registers, which is then modified into working in the context of running in EL1 instead. So we end up with this, in addition to our EL2 system register array, we end up with this shadow system register array. And then the way we did that in terms of the code is that whenever you're entering the VM, we look at the mode of the virtual CPU. We say, if it's running in EL1, we'll set up a pointer that points to the normal system registers, and then all our complicated world switch functionality can just follow that pointer and take all of the EL1 system registers and put it into the hardware. But if you're entering the guest hypervisor in virtual EL2, then you'll set the pointer to point to the shadow system register array, and then things just work. We also need a way to enter and exit the guest hypervisor. And what that is, it's really emulating virtual exceptions. So what happens is if something running in the VM in EL1 should trap into the guest hypervisor, it will do some sort of privileged operation which traps into the real hardware EL2 mode where the host hypervisor runs. And the host hypervisor will then emulate that exception in software and change the mode of the virtual CPU and just return to the VM, and that will then return the shadow state and run your virtual EL2 instance. You also have the other case where you want to go from the guest hypervisor into the EL1 or EL0 modes of the VM. And here we rely on the feature from ARM v8.3 that we trap on an exception return to the underlying host hypervisor, which then emulates the behavior in software similarly. So a hypervisor that runs on real hardware will rely on having stage 2 MMU virtualization, or having stage 2 MMU, which is similar to EPT on x86. Right? So now we're running that inside a VM, so now we have to virtualize the stage 2 MMU. So basic virtual memory, hopefully everybody here is familiar with that concept, is you translate virtual addresses into physical addresses. On ARM, the result of the first stage of translation you can do is called IPAs, or intermediate physical addresses. And they're called that because if you run VMs, you have a second stage of translation in the hardware where you translate the intermediate physical addresses, or the IPAs, into real physical addresses, right? And that stage 2 translation is managed by your hypervisor, and that's the basic VM case. If you then do nested virtualization, you want to tell the guest hypervisor that it has stage 2 translation, and it wants to use that to isolate its nested VMs between each other and to protect what memory they can access. The problem is you only have 2 stages of translation in hardware, but you're really going to need 3 stages of translation, right? So what we do is we use shadow page tables, and we tell the guest hypervisor, you can just go ahead and program your virtual stage 2 page tables, and then we build a shadow page table on demand. So whenever we see a fault from the nested VM in the host hypervisor, we go and walk the virtual stage 2 page tables in software, and we combine that level of translation with the existing information that the host hypervisor has on how to map a VM, not a nested VM, but a VM IPA to a real PA. We put that entry into the shadow stage 2 page table, which is the one that the hardware MMU then walks. And then you rely on trapping on TLB invalidations to keep everything up to date.
Sorry, quick question.
Sure.
Wouldn't it make more sense to speed this up and just have a single bit which is specified by the index, and you know this bit in the address page is actually the bit that specifies this virtual stage. Basically have a virtual intermediate VV IPA.
So the question is if we can.
On a hardware level, basically.
So the question is if we can extend the hardware to have some extra bit to provide an extra level of.
You have a register which is an index, and it tells you this bit in the address of the page is actually the bit that tells you is this IPA or it's a VIPA.
So I think my answer to this is you can surely expand the hardware and the architecture to somehow have support for 3 levels of translation in one way or another. If you have a good idea for that, I'd love to hear that afterwards and try to understand it. But that's not what you have with ARM v8.3.
Yeah, that was the question.
I think TLB means it's become really expensive if you have to work 3 levels of page table.
Yes.
It's exponential. I mean, if you have 3 levels and 3 levels in the page table 3, you have 3 to the third, not 3 times 3.
But it's only used in the case, it's basically only, okay, we
So
talk.
TLB misses are already much more expensive with
Okay, maybe
All right.
I'm going to refer
2
to the
levels
question
of translation.
is
If
there
you have
something
3,
in the
it becomes
8.3 that was meant and you said no?
So 8.3 gives you the bare minimum so that you can just do this. I'll talk about performance in a bit as well. So then you can. So actually, the shadow stage 2 page tables is not really the biggest issue. I'm sure it is for a particular set of workloads. Okay, so that was shadow page tables for stage 2 MMU virtualization. So we also need to give the guest a hypervisor timer. So ARM provides a virtual and a physical timer in EL1, which is what we normally give to a VM. EL2 has its own timer called the hype timer, and now when we tell the VM that it also has EL2, you also need to give it a hypervisor timer. We don't have an additional timer to give it in the hardware, so what we do is we multiplex the hypervisor timer onto the timer that the host hypervisor uses and emulate it in software. And then we have nested virtual interrupts. So ARM has this feature, the GIC, the ARM generic interrupt controller. It's an architecture for how to do an interrupt controller. And I try to never talk about ARM virtualization without talking about the GIC because we all really, really love it. the basic idea, so this is super, super oversimplified. The basic idea is you have some device lines going into the interrupt controller, and the interrupt controller figures out which CPU should then get an interrupt when a device raises an interrupt. Right? And so you have a line from the interrupt controller, from the gig to the CPU, that signals an interrupt, and then the CPU can acknowledge, which means I'm taking this interrupt and figuring out what it was, and EOI it, which means I'm going to tell the interrupt controller I'm done with this interrupt. You can signal me a new one. The gig has support for virtualization. And the way that that works is that you can signal virtual interrupts to CPUs using a dedicated virtual interrupt signal to the CPU. And the CPU can then ACK and EOI those virtual interrupts without trapping to the hypervisor. Virtual interrupts don't come from physical devices. They typically come from emulated devices, so they're programmed by software. The way that that works is that the hypervisor can write into special registers on the gig called the list registers and say, please signal this virtual interrupt to the VM when it's running. In terms of nested interrupt virtualization, what we want is we want to deliver virtual interrupts from the host to the VM for the first stage. So we do that as we do normally, and what that really means in terms of nesting is that we're delivering virtual interrupts to the guest hypervisor. Right? If you're running a hypervisor on hardware, the thing that will get your interrupts, the physical interrupts, is your hypervisor. So now when you deliver interrupts to the VM, you're really delivering interrupts to the guest hypervisor. But we also want the guest hypervisor to be able to deliver interrupts to the nested VM using the hardware features of the gig, so that the nested VM can ACK and EOI these interrupts without trapping. So the way we do that is, again, we use this concept of shadow registers. We do that with shadow list registers. And what we do is we let the guest hypervisor program virtual list registers. We tell the guest hypervisor that it has a gig, which it really doesn't. And then the host hypervisor then translates the values, makes a copy and translates those values of the list registers into the real list registers, which they then use, or which it then uses when you run your nested VM. So the result is the nested VM can then ACK and EOI virtual interrupt without trapping. Okay, so performance. That's an interesting one with nested. The problem again is we don't have any 8.3 hardware. I said this morning we don't have 8.1. We certainly don't have 8.3. So again, what's the solution? Well, we can tinker with software to get an idea of how this is all going to perform. Right? So what we did is we paravirtualized the guest hypervisor to change all the instructions which don't trap on 8.0 to actually trap. Right? So we replace a bunch of instructions with hypercalls. And actually the insight is that that really closely emulates the performance if you took a current platform and then you added 8.3 support to it, right? Because a hypercall instruction, the cost of that is going to be really, really similar to trapping on any other instruction. And then we modified the host hypervisor a little bit to deal with that. So if we look at the hypercall microbenchmark, talked about this morning as well, but the idea is you make a hypercall from the VM kernel, and you read the cycle counter just before you do that, and you wait until you get back, you read the cycle counter again, and that's your benchmark output. For a normal VM, that's how that works. For a nested VM, you do the hypercall from within the nested VM, and you wait until the guest hypervisor handles it, and then when you come back, you know your result. So it looks like this. So we have a little less than 3,000 cycles on a normal VM and a little more than 400,000 cycles on a nested VM. So that's a slowdown of 155-ish. Why is it so slow? So just briefly, this is just a primer. I'm going to go into application level workloads in more details later. But this is, the blue bars here is normal VM performance, right? And the orange ones are nested performance, right? So it's pretty horrible, like more than 40x. So let's try to figure out why it's so bad, okay? So if we look at this VM to hypervisor transition thing in a little bit more details, we have the initial VM exit from the nested VM kernel, which goes to the host hypervisor and then into the guest hypervisor. And then at some point you return, okay? But in between these 2 points, the guest hypervisor does some work. And part of the work it does is it will access a lot of EL1 registers. And each of those cause traps. And it will also access some EL2 registers. That also traps. Okay? So with one trap, you end up with a lot of traps. And that's known as the exit multiplication problem. Okay? I think that's what the turtle guys who did Nested Virtualization x86 originally called it. So we end up with more than 120 traps for a single hypercall from the nested VM. And this is the main cause of your terrible performance. So to improve performance, we somehow have to reduce the number of traps. Okay? So what we did was we looked at the traps and we went, okay, all of these traps are related to system register accesses, and they belong to really one of two categories. I messed up my slides, sorry about that. So what we did was we took that insight into those two categories, and then we prepared an architecture proposal that we called Neve for Nested Virtualization Extensions for ARM for how to modify their architecture to make the performance better. And it uses register redirection to do that. So the first category of these registers that we access from the guest hypervisor, which traps all the time, is EL1 registers, or VM registers, right? And what they are registers that control the nested VM's execution, but not the guest hypervisors, okay? So the insight here is that when you go back and forth between your guest hypervisor and your host hypervisor a lot, you don't actually need the results for anything in terms of the current execution until you return into your nested VM, right? So if we can somehow just lock what happens or defer the effects of what you're doing until you actually return to your nested VM, you can do better. Okay? So that's exactly what Neve does. Without Neve, when we issue an instruction to access a register from the guest hypervisor, you'll cause a trap. But with Neve, we'll redirect that in hardware transparently into a place in memory. Okay? So whenever you enter your guest hypervisor, the host hypervisor will fill out this table with your values of registers, and then the guest hypervisor can read and write registers without trapping, and they just get stored in memory. But there's another category of registers, which are hypervisor control registers. These are typically EL2 registers. And we can't do the same trick with rewriting them to memory because they directly affect the hypervisor's execution. So what we do here is we look at, well, what happens when you do trap on those registers? Typically what the host hypervisor will do is, if you consider a write, for example, it will take that value and write it into an EL1 register, just as it is. So for all those registers, we can avoid the trap by simply redirecting EL2 registers to EL1 registers, right? So that's somehow the opposite of what VAG did that I talked about this morning. So now you get a combination of both, which is really interesting. So if we use this technique and look at the results again, we see that we go from these 400,000 cycles into around 90,000. So better, we go from 155x to 34x. Again, significantly better. 34x may sound bad, but in context of nesting, not that bad really. The trap count is significantly reduced, right? So the application level workloads that I showed you before are, kernel bench, hack bench. We run spec.jvm, MySQL, memcached, netperf in various configurations, Apache, and Nginx. And we ran it on both ARM and on x86. Okay? We used APM-XG, and it's a bit of a dated platform now, but that's where the work was done. And we used an Xeon E5 2630 for the x86 platform, which has VMCS shadowing and that enabled while we ran our workloads. These are reasonably similarly configured machines. And when we ran these workloads, both for the native and for the VM and for the nested VM, we always made sure that the unit running our workload had 4 cores available to it, 12 gigs of memory. And we chose those numbers so that the next level hypervisor would always have some reasonable amount of resources. So for example, for the nested VM, you'd have 2 dedicated cores on your host hypervisor, 2 dedicated cores on your guest hypervisor, and then 4 dedicated cores for your nested VM. And we used VirtIO for all I/O stuff here, over 10 gig Ethernet. And this was all done with KVM on KVM, of course, and based on 4.10. So this is pretty much the same graph that I showed you briefly before, but here we have the green bars, which are our nested results. So the blue again is VM, and the orange is nested. And this shows, like this morning, overhead normalized to 1 for native performance. So lower here is less overhead and better. Okay. We show this split graph with 2 different scales, just because the overhead is so high that we have to do that, right? And what we see is that the overhead is still high, but some of them, like Apache, for example, is reduced really a lot, so it becomes usable. Right? And if you do like a raw network throughput with VirtIO benchmark, you get 10x better performance. But we also compare to x86, so those are the red bars. And really my takeaway from this is that, okay, nested virtualization overhead is high, right? So with Neve, we get ARM, again, sort of on par with x86. Sometimes x86 is a little better, sometimes a little worse. People use nested virtualization on x86. So ideally, you can use nested virt on ARM with 8.4 as well. Because Neve, that we proposed and wrote up as an architecture proposal, has really been the foundation of an extension or an improvement for nested virtualization that's going to be included in ARM v8.4. So we have an implementation of KVM ARM for 8.3. We've evaluated the performance using a paravirtualization technique to emulate ARM v8.3 behavior on current ARM v8.0 behavior. That seems to be a good trick in the ARM world. Due to the exit multiplication problem, we get really high overhead, but Neve does a lot better by reducing the number of traps. And we wrote a paper about this, which is going to appear on Monday, I think, in SOSP in Shanghai, if you want to read more about it. There are patches on the list. We have the nested CPU virtualization patches are in really good shape. They're in V2. I think we can safely drop the RFC tag. The nested memory virtualization patches, there's one version there on the list. It needs some review. It needs some love. And we have all of this 8.3 and Neve paravirtualization stuff all publicly available on GitHub. And there's some QEMU patches to control whether you want to start a VM with EL2 or not, and that implemented. So that's it from me. Questions?
What do you do for APIs with the git control? Does it actually go through the hypervisor?
So the question is, what do we do for APIs? So you mean virtual APIs between vCPUs in nested VMs?
Yes.
So what happens is the nested VM will try to write to the interrupt controller. That will cause a trap to the host hypervisor, which will see what is this thing trying to do, and it say, okay, it's trying to access some memory outside this memory area, but not something I should handle because I have a guest hypervisor. So it'll emulate an MMIO fault into the guest hypervisor. The guest hypervisor will then figure out, oh, this is the nested VM trying to access the emulated interrupt controller. So it will go and update its virtual list registers of the gig and say, okay, here's an IPI for this other thing. It will then, once you return, because you trap on the ERED, you go back out to the host hypervisor, will then says, oh, the virtual list registers was changed. Let me update my shadow copy, put that into the real list registers that I'm going to use when I run my nested VM, and that will signal a virtual API to the other virtual CPU.
Okay.
Yes? Was the shadow paging code written from scratch, or did it exist from before there was two-level paging in ARM?
So the question is if the shadow page table code was written from scratch, and the answer is that yes, it was. That's actually an interesting implementation thing, because initially I wrote that code, and initially I looked at it and I went, okay, let me try to express shadow page tables in terms of, or page table walk in software in terms of Linux concepts of page tables. But then you quickly realize, okay, stage 2 pages are different than the pages you use for the kernel, and also the configuration that you run your kernel on may be completely different in terms of levels and stuff than your guest hypervisor. So writing that code sort of from scratch by hand, all of a sudden it just becomes very, very tedious. So what I ended up doing is there's a piece of pseudocode in the ARM architecture reference manual, right? And I very closely modeled it to that and put a comment that says this is where we do something slightly different because it's not pseudocode but real code. So it looks a little bit cryptic. Like you actually can understand it once you go through and debug it enough. But if you compare it to the architecture reference manual, it's very close. So that's the way we did that. Yeah.
Follow-up question: Is it serialized like the x86 shadow page table code, or can multiple translations be updated concurrently as long as they're kind of in different regions of the address space?
The question is if the shadow page table code is serialized.
Updates to the translations.
If updates to the shadow page table codes are serialized with a lock,
okay.
Yeah, per shadow page table, yes.
Okay.
I think we ran 2 nested VMs and 2 guest hypervisors just to check that it works, but with no performance measurements whatsoever. So once you start having hardware or people start using this more, and I'm sure that you'll find numerous slow paths that you can optimize a lot. We also looked at in relation to your question, we added ARM app functionality, which we didn't have on ARM. And basically a lot of the ARM app that they use in x86 is really embedded in the x86 code. And the initial prototype just copies a lot of it and copies it in. But yeah, I think there's room to share some code and improve that a fair bit. Yep.
How does Nested VM play with hardware isolation? Because now if you trap to the host hypervisor, you means that basically you're skipping any level of sanitization that the guest is doing. You're basically allowing the nested VM to trap to the host, basically to the host hypervisor. So basically you're forward. So how does that play with the trust zone, with hardware isolation?
Trust zone is on the secure side, has really nothing to do with virtualization. It's a really, you have a, it's something else.
But if you put the guest into a normal world, right? It's isolated.
It can only be in normal world. Virtualization only exists on that side.
But the point is that now you can have a nested VM which has gone evil, corrupt, exploited, doesn't matter, and you trap it to the host.
Yes.
Yes, the host, so the question is, what do you do in terms of sanitization? How do you protect the hardware and do isolation when the nested VM can...
forward and interrupt to, let's say, to the hardware and stuff like that, it's
when the nested VM can trap to the host hypervisor. And the answer is that the host hypervisor really has to manage your underlying hardware, and it is the one that fundamentally has to provide you protection and isolation. And now when you support nested virtualization, it does have to realize that there can come traps from a nested VM, and it has to sanitize those and deal with that. So we don't, for example, verbatim take the list registers and write that into the hardware. That's why we have shadow list registers. And we have a function that goes through and says, is this something that I can validly put into the hardware? This is the fundamental job of the host hypervisor that has to manage the underlying hardware. So that is what you rely on. Sorry?
This is taken into account. That's the
Yeah, I mean, I won't claim there are no bugs, but sure.
You need to ensure the same level of isolation that the hardware L2 would provide.
yeah,
So
that's the question.
you have to go, basically you have to go through all the system registers that you emulate and provide the exact same level of guarantee because you're effectively doing L2 in software.
Yes.
Yeah, we're talking
So
about
that,
the same thing.
so that's the discipline of writing hypervisors in general, I think. Yes, question?
Early on, you had a slide talking about what was added in V8.3, the kind of the three fundamental things
Yes.
to support nested virtualization. The third one to me seemed out of place. It was basically what you were doing with Neve, which was saying you didn't have to do this trap to tell the nested hypervisor that, hey, don't worry about it, you're nested. I'm curious.
So-
why do you think ARM added that one?
So I think I can rephrase your question a little bit if I may. Right, so I think the question is why does the hardware lie to you when you read the current exception level as opposed to trapping when you read the current exception level? And I think that's just because it's a super trivial change. And maybe somebody thought it's a very common operation and they just did that off the bat. Yes?
Does this extend to deeper levels of nesting if you virtualize the 8.3 extensions for your guest hypervisor?
Yes. ARM v8.3 is recursively self-virtualizable, I think is the academic term. This was also described in the 70s, by the way, what you need to do to make this right. And now they do. And Neve, the 8.4 stuff, is also self-virtualizable and recursive, and it does speed up execution of multiple levels of nesting. Yes. Yes?
How did you test this Neve extension where the registers are written to memory instead of trapping? I mean, you certainly did it paravirtualized, I guess?
Yes. So the question is, how did we test? And I assume you mean how did we evaluate the performance?
How do you write the values now? Is it in the guest hypervisor? Or?
So the guest hypervisor will read and write memory. It would just replace the instruction with loads and stores to a specific offset into memory. And then we set up an agreement method between the host hypervisor and the guest hypervisor to figure out which page we store the whole thing in. So it's very close to what would happen in real life, but yeah, it is.
Okay.
Peter.
How do you handle things like PSCI? How do you tell this is an HPC that gets to go to the nested hypervisor or it should go to the transfer?
Right. So the question is, how do you handle things like PSCI, which relies on a guest, which is for power control for stuff like shutting down your CPU and starting it, where you issue hypercalls currently from the VM to the host hypervisor. And we sort of take, and so the point is, if you do a hypercall from the VM, is it from the nested VM? Does it go to the guest hypervisors? What if the host hypervisor does, the guest hypervisor does a hypercall? Where does it go? And so on. What we do is we take a bit of an extremist point of view, and we say, well, we're emulating a machine which has EL2, and on a machine that has EL2, if you issue a hypercall, the hypercall goes to EL2, right? So the the hypervisor can perfectly well make hypercalls to itself. So hypercalls inside a VM is now handled by the guest hypervisor. ARM v8.3 also says that no matter what, if you do a secure monitor call, which is what hardware would do to manage real hardware, that always traps the host hypervisor, and that's what the guest hypervisor would have to do to turn off a CPU, for example. Sure.
How did you deal with the fact that there is no VHE hardware?
How do we deal? The question is, how do we deal with the fact that there's no VHE hardware? And that's a really interesting one, because actually, you can run a guest hypervisor that uses VHE on hardware that doesn't have VHE, because you're running it in EL1, and what VHE gives you is that you can run something for EL1 in EL2, right? But now you're running the one thing for EL1 in EL1. So that's how we dealt with it.
What was the question?
Can you migrate a nested hypervisor?
Can you migrate a nested hypervisor? That's a really good question. I think you can if you just expose all the state you have in your kernel to user space so that it can transfer all the state. I don't see why you wouldn't be able to do that, but I haven't thought carefully about it. Okay?
And the x86 to ARM comparison, the x86 had twice the RAM of the host. That is inconsequential, or did you do that because of some?
So the question is the differences in the amount of memory between the x86 and the ARM machine, and we limited the amount of available memory, and we also disabled hyperthreading on x86 because there's no hyperthreading on the ARM platform. Yep.
Yeah. Well, probably a follow-up question. The AMD implementation of nested virtualization is pretty different from NT. Did you consider trying to use that as also a benchmark for a performance comparison? Because as far as I know, I might be a bit outdated there, but there is significant difference between the two.
So the question is if we considered running measuring AMD platforms as well. So as far as I'm aware, the big difference with AMD is that you don't trap when you access the VMCS in the guest hypervisor. Correct me if I'm wrong. But we did use a recent Intel CPU that has VMCS shadowing, which addresses that same issue. So I think they're more similar today, but I'm not an expert on x86. It would be interesting to run. I didn't have time or a platform available, but it would be an interesting measurement point for sure.
So one difference is that AMD doesn't have the nested virtual interrupt controller, while Intel has nested virtual interrupt controller, so it would probably be slower. And also, I've never really seen why, but it's much slower to do VM exits in AMD than in Intel. I think it's because in Intel it's just okay. There are the pointer load and pointer stores that Shadow VMCS take care of it, but on Intel it's just VM resume. On Intel you have VM load, CLGI, VM run, STGI, VM save. So you have 5 exits to do emulation compared to one on Intel. But the new, I think it's the EPIC processors, the one that just came out, have a virtual VM load and virtual VM save, virtual CLGI, virtual STGI. So with those processors, it should start to be comparable. But for now, as things stand with most available processors, it would be probably even worse than.
Right. So if somebody has the time, it would be a very interesting data point.
But only on new processors, otherwise it
Okay.
would just suck.
I saw a question.
No, we played with virtual STGI and virtual VM load back then, so we were just detecting the entry and exit path from KVM and just basically did the whole sequence in the host. And that basically gave me negligible performance difference.
So it seems like everybody thinks that it's going to be close, but somebody should measure it. Final question, I think?
Yeah, so when you're talking about the guest host accessing registers that are privileged and they go back out to the host hypervisor and kind of that ping pong,
Yes.
consider having some paravirtualization interface, like adding an HCall or something from the guest hypervisor to just make one call, I want all these registers.
So we did think, so the question is if we consider paravirtualizing more significantly, I think, to improve performance. And we did consider, and I think Alex also suggested that back in the day, that you could basically rip out all EL2 of your guest hypervisor and do one hypercall to say, I'm just going to change from this context to another context. You definitely could do that. I just think that one of the really interesting things about doing nested virtualization is that you can debug your hypervisor and develop it. And if you're debugging something that's entirely different and that's not doing any of the low-level critical stuff, which is really hard to write, the whole point kind of goes out the window for me. So yeah, and it's a fundamental question. If you don't care about unmodified guest hypervisors, then for me, I get a little bit into the why you're doing it in the first place. Okay, thank you very much.